Today we're going to take a look at sinusoidal regression. Sinusoidal regression just means trig. Okay, so sinusoidal is a fancy word for trig, but it means that our graphs are going to behave in that wave pattern. Regression simply means I've collected data that behaves like a certain pattern. Doesn't always line up perfectly, but it does behave like one. So we're going to be using Desmos today. For regression, I want you in just regular Desmos. So notice the banner is black, not green. It's got open features that your testing Desmos doesn't have. So the one that you used in Math 1 or Math 3 doesn't have these features. So Professor Barney and his assistant Otis are trying to decide where to spend their spring break. Barney favors Chicago. Otis likes to go to Honolulu. Using the information given in the table below, help them make a decision. The table gives the normal daily high, so the highest temperatures in Honolulu and Chicago. For each month, T equals 1 represents January. So X being 1 or T being 1 is January, February, March, April, May. And then they gave us those high temperatures. So let's start with Honolulu. So when you're working in Desmos, if you have information like a table, we want to add that. 2, 3, all 12 months, and then you go in and enter your data. Here's the data, 81.1, or 80.1, 80.5, 81.6, 82.8, 84.7, 86.5, 87.5, 88.7, 88.5, 86.9, 84.1, and 81.2. So I've got all 12 months worth of data entered into my table. If you look on the left-hand column of your table, there is a blue selection bar. At the bottom of that selection bar is a little magnifying glass. If you click the magnifying glass, what it will do is auto adjust your screen to display all of that data. But if you notice up at the top of your blue bar, they have this like 4 dots with a line that goes through it. That's your regression. So if you click that, this is a new feature in the Open Desmos where the regression will build itself and it's got a drop-down menu for you to select what you want. So you click that and you have linear, quadratic, cubic, quartic, but at the very, very bottom, you have sinusoidal regression. And it will build a model, a prediction model. If you notice these data points that were collected, they kind of follow that behavior, but they don't always line up perfectly. And that's because, predictions are just that. They're just a prediction. What actually happens is entirely up to nature. But if you look right underneath the drop-down menu where it says equation, it builds an equation for you. So here's your prediction model. So it says find a trigonometric model for Honolulu. It is 4.24 sine 0.51 x. I'm just kind of rounding to 2 decimal places. Minus 2.44 plus 84.3. So here's, 3, 4. Here's the model for Honolulu, and we want to do the same thing for Chicago. So when you're using the locked Desmos, you'd have to erase all of your work. Here we have the ability to turn it off by clicking the colored buttons, but we don't lose any data. So here's my points for Honolulu, and I will actually turn those purple so they match my graph. And here, I'm going to build a new table, and this is going to be my table for Chicago. So I just re-enter January, February, March, April, May, June, July, all the way through December, and I put Chicago's temperatures in. All right, here we go. All of those are in, and you can, use those same regression buttons and the same magnifying button. So I'm going to actually go to where all my blue data is. I have not gotten rid of Honolulu. I just turned Honolulu off. Here is Chicago. I want to create a regression model. So I click that regression symbol, and we want sign regression. So here is the model for Chicago. Right here on the lower section of your Desmos is where you will find your regression um, equation. So for Chicago, I would write y is equal to 28.58, yada, 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 yada. I don't have the space, so I'm going to just leave it in my Desmos. So I have the black, which represents Honolulu, and the blue that represents Chicago. I'll make this one blue for Chicago, and I'll make this one purple for Honolulu, so it's all the same color all the way around. Okay. So all I'm going to do, I'm just going to turn it off. So it says using a graphing calculator, that's our Desmos, and the data points and the model for temperature in Honolulu. How well does the model fit? Okay, so I'm going to look at Honolulu, and I'm going to look at all the points on Honolulu. So if we look at it, how well do those points fit? Is it a pretty close match? Is it not a close match? Looking at this, we do have an R squared down at the bottom of your box. That tells you how like closely related those points are. It is not a percentage, but if you think about it like a percentage, that tells you that like this is 97% strong. Like the strength of this model is 97%. So I would say it's actually really close to um, the model. The data points are very close to the model. Um, and you can kind of, with your eyeballs, you can see those dots don't line up perfectly, but they follow the same pattern. So it's a good representation. And this is how like weather people make those predictions in temperatures is they're looking at what's currently happening, what kind of model does it best fit, where should this go. Using the graphing calculator to graph the data points and model for Chicago, how well does the model fit? So I'm going to switch from Honolulu, and we're going to take a look at just Chicago. Okay, so here's my model. Again, my R squared value, that's like 99.7, which means, again, it's not a percentage. Mathematically speaking, it's not a percentage. But if you think about it like a percentage, then you can, that kind of gives you that measurement of how close that data fits. And it's about 99% accurate. So it says, how does the model fit? Um, I would say it fits. I personally would say it fits really closely. The dots don't line up perfectly with the model, but they're very, very, very close. Use the model to estimate the average annual temperature in each city. So if I look at Honolulu, okay, you have highs and you have lows. The average is the middle of that data. Like, what is it typically? Okay. So if I look at this graph, I know that the average of it would fall where my midline was, or in the middle of my data. So if I look at my equation, my midline should be about 84.4. Let me do, so I'm going to use my equation, this here, okay, that we did for Honolulu. That's going to tell me what my graph should look like, or where my graph should have its midline. 84.4. So visually, we can see here's the middle of my graph. So on average, the temperature should be about 84, degrees. Honolulu is about, I would say, 84 degrees based off of my midline. And it says, which term of the model did you use? We used that midline because it's the middle of the data, the middle is average. So for Honolulu, I'm going to turn that off. And for Chicago, come down here to Chicago, turn all my data for Chicago on. According to my regression, my midline, my last value, that would be, I'm looking here at my equation, the K value or the midline looks like it's close to 55.7. So if I come up here, and this is, you don't have to graph it, but it's just for visual. It came from our regression. Right there's about the middle of my graph. We have temperatures that are higher than that, temperatures that are lower than that, but that's right about the middle. So I would say about 56 degrees. And again, we use the midline. We had to use the midline because it is the middle of our data, that average value. What's the period of each model? So again, period means the amount of time or the space for it to complete one hill and one valley. Or it has to go, excuse me, it has to go up one time and down one time. So I'm already here in Chicago, so I'll stay in Chicago. If I look at this, here's my midline. So your period, it's easy to count when it starts at your midline. Okay. So we're going to start at the midline and we're going to travel up. We're going to complete one hill and one valley, and we stop here. So we started at 3.8 and we finished at 17.1-ish. Okay. I'm going to just round. I'm going to say it's close to 4. We started at close to 4 and finished at 17. Again, just rounding to help with the number crunching, which meant my period for Chicago was 14. Our X axis is counting by months. So I have a period of 14 months. So that cycle of temperature should start to be predictable after 14 months. Let's go and look at Honolulu. We turn off these data points. At Honolulu, if we zoom in, the middle of this graph we said was about 84 degrees. Yeah, something like that. Here in this graph, trying to zoom in, goodness. Here in this graph, I have a midline. So that's kind of where I like to start. So it's about 4.5. And we're going to travel up one hill, under one valley, and end at the midline again. So we started at a hill, or we started at our midline. We went up the hill, through the valley. So we've completed one hill and one valley, and we end at 16.9 or almost 17. So if I look at my period for Honolulu, it's about 4.5, and it ends at 17. So that puts it at almost 12.5 months. Depending on like how you round, it's just a rounded number. It's close. Okay. which means that if we were in Honolulu, about every 12 and a half months, your weather pattern becomes more predictable because it's a new cycle of the same thing over and over and over. The same way here in Sanford, we get winter, and there's probability of getting snow almost every few Februarys. It gets cold enough for snow just about every February, or sometimes it's a little later in March, sometimes it's a little earlier in January, but we can kind of predict when the ice is coming and when the snow is coming. Same for hurricane season. We know that in the hurricane season, that runs, I think, July through November or June through November. We can start predicting when the hurricanes hit North Carolina. Um, and, based off of weather patterns and things like that. Which city has the greatest variability in temperature? Okay, so if I'm looking at these, let me put both models back up here. Here we go. Purple is Honolulu, and blue is Chicago. Turn that midline off. If we're looking at these, it says which one is more has more variability. Which one changes more? Well, Honolulu is very low. The one that, the temperatures vary a lot more is Chicago. They have very warm temperatures at 84 degrees, but they also have very cold temperatures, 27 degrees. But if we look at Honolulu, too many dots. Oh, Lordy. Oh, if we look at Honolulu, their lowest is 80, their highest is 88, 89 degrees. So the temperatures only vary by 9 degrees. Where here in Chicago, we're looking at almost just under 60-degree difference, like 50 something degree difference. So Chicago's a lot more variable in their data. And the key feature that we're looking at that determines variability is the amplitude. The higher the amplitude, the more spread out the data is. The smaller the amplitude, the closer the data is. So if spring break is in March, which city would be best? Okay, so we've got both of our data here, and we want to know what happens in March. So if I'm working in Desmos, my first question is, according to my table, is March going to be an X value or is March going to be a Y value? March is a month, and so I know that that is X, and March is January, February, March, the third month. So if we went to Chicago, it'd be about 45 degrees. And if we went to Honolulu, it would be 81 degrees. So where should they go for spring break? My opinion, Honolulu. Also, why would they choose to go to Chicago if they had the ability to go to Honolulu? Beats me. So what we're doing is we're creating a model that allows us to analyze, compare, make predictions that are no longer on the table, those kinds of things. So let's do maybe one more here in our notes. I gave you a bunch, but it's just to be able to have a data set. Um, let's look at that's temperatures in Chicago, precipitation San Francisco. Okay, let's look at this one. Number one. I'm going to clear out all my Desmos so I have a nice clean slate to start with. Okay. The following table shows the number in millions of unemployed people in the labor force from 1984 to 1995. So last century. That's sad. Last century. Um, I was born here, so I'm very old. So let's look at these. And it says enter the data in your calculator and get a scatter plot with x equals 0 corresponding to 1980. So 84, this would be year 4, 5, 6, 7, 8, 9, 10, 11, 14, and 15. So they don't want us to use the actual year. They want us to use years since 1980. Okay. So I'm going to create that very same table in my Desmos. So year 4, 5, 6, 7, 8, 9. We are going all the way to 15. And we are putting in the number of unemployed humans to the millions. Eight point three two 8.237, 7.425, 528. So while we're entering this data, um, if you notice, the unemployment rate has starts off at 8.5, it goes lower, and then it begins to climb again. So when we're studying things like economics or recessions and depressions, things like that, our nation's economy fluctuates. Sometimes our nation does fantastic as a whole in terms of, um, sustainability, employability, um, income in, income out, based off of trades and goods and things like that. But when our country is doing very well as a whole, our unemployment rate is lower. People are able to work, they're able to get jobs, they're able to take care of things. When there's a crisis in the economy, people get laid off, um, or, you know, the pay is reduced, or there's inflation. So maybe they're not losing a job, but maybe the economy, like think about when you go grocery shopping today, um, or you go shopping today, the prices are really high because of inflation. Well, people's paychecks don't change. So when, things were really cheap, their money went a long way. When things get really expensive, their money doesn't go as far. And so they have unemployment. So unemployment um, models like this, ooh, I zoomed a little bit too far. Unemployment models, um, they give us an idea of what's going on in the economy. How do we prepare for that? Um, and then, how do we react to that? So here we go. Just a little side note. Does the data appear to be periodic? Meaning, does it appear to go up and down and up and down and up and down? My opinion, yes. It says find the model. If so, find a model using sign regression. So I'm going to go to my regression button and I'm going to do my drop down. I'm going to come to sign. And again, it follows the pattern, does not line up perfectly, and that's okay, because if what happened in reality lined up perfectly with a model, there would be no surprises, or there would be no opportunities to be different or do different. So we have our model. I'm looking at my R squared value down towards the bottom. It's about 8.7, so about 87% strong, which is pretty good. It's a pretty good model. Okay. Do you think the model is likely to be accurate much beyond the year 1995? So at year 1995, that's 15 years in. That's also the end of our data table. So what it's asking is if all we have access to are the black dots and a model, do you think we could still use the model to make predictions past 1995? I say yes. And then why? Well, if we follow this, those black dots follow closely to this pattern. Again, not perfect, but very closely, which means that when we move outside of the window of those black dots, that pattern still happens over and over and over. This is also why we spend a long time studying like history, American history. And we have that phrase like history's bound to repeat itself. And that's because it's periodic. You can see it in the economy. We've had ups and downs. We've had war that comes in and out. We have civil issues that happen cyclically or periodically. Um, so this model, even though not perfect, kind of gives us an idea of what it would be like in the future. What is the period of this function? So it's periodic, meaning it's back and forth, back and forth. I first need to figure out where's the middle. So my regression gives me that. It's at 7.7. So I will, ooh, wrong spot. Try to get that graphed for you because that gives us an idea of where to look for my period. Okay, here we go. There's the middle of my graph. Okay, there's a lot of points going on, so I'm going to go to a nice clean space. So here is my midline at 18, when x is 18, and I'm going to go through one hill and one valley. Scrunch it down just a little bit. So one hill and one valley. Ooh, we have froze. One hill, one valley, and we end at 25.9 or 26. So we started around 18. We finish at around 26. So that is a difference, 18 and 26, of 8. So the period is every 8 years. So every 8 years, you're going to experience a high in the economy and a low in the economy, or a high unemployment and then a low unemployment. What is the average number of unemployed people, and what part of the model do you find that? So if we look for the average is what's happening kind of in the middle. And so we have about 7.7 million unemployed workers in the United States at any given time. So let's actually kind of stop here for a second and just look at, does this model tell us, is it accurate? Is it telling us what's going on, let's say in 2025? That's this year. If the model started in 1980 and we're going to look at 2025, that is a difference of 45 years. Okay. Okay, so here's our data. I'm going to close this off. Here's our data. We don't have any 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 data. We're moving over. Okay. 2025, let's assume there's about 8.3 million unemployed individuals. I'm going to put my midline back. Here we go. Ooh, not that one. This one. Okay, so 7.7 is average, right? Whether it's a good year, it's a bad year. So in 2025, according to this model, there are 8.3 million unemployed individuals. If we look at it, there was a lot of unemployment, which meant that there was an economic crisis. Okay. Ask your parents, or maybe even some of you have experienced, there was an economic crisis not too long ago. We had COVID. That really hit let's see, that was year 43. So that was 2023. Let's see, 35, that was 2015. So we had COVID. We also had like an economic crisis here. Inflation happened here. So when inflation happened, unemployment went up. So we have an economic crisis. We had a lot more people unemployed. And according to the model, okay, here's 20, according to the model, not that this is really happening, but says that we should be coming out of an economic crisis and heading towards normal. So at the beginning of the year, there are 8.3 million. By the end of the year or halfway through the year, there's 7.7. So it's predicting that we should be coming out of an economic crisis so that there's less unemployed and going into a a peaceful economic crisis, or that the economy should be doing a little bit better because we'll have less unemployment happening here. Whether that's true or not is entirely up to the government and how economics works, but we can use this model to make predictions. Um, Again, you have other tables that you can kind of practice with. We're going to stop our notes right there. You do have a project that you're going to be working on today where you research a city of your choosing and you collect data from 2022, the whole year. And then you're going to, create a regression model. You're going to make a prediction of what the weather would be like a year from there. It is a paper assignment. So you're going to each collect your own. I have a website in Canvas that you can use. Let me see if I can find it. And you are going to pick a city of your choice. Please, please, please don't pick Sanford. Pick something better. Wait, Sanford's okay. Okay. I'm not going to lie. Sanford's okay. But pick something extravagant like Paris or, you know, Tibet or something interesting. You go to modules. It's at the bottom of your modules. And it's called Climate Tracker. See if we can go to it. Basically, it's a website that has collected data from various cities over several years, and it's got the temperatures. So you're going to pick a state. Um, let's pick, I guess this is just locked into the United States. So pick somewhere cool in the USA. Here's a place that's not cool, Ohio. Okay. Pick a city, Columbus, Ohio. And your parameters are average temperatures. So we want them to measure by month. We're going to start with January, and the year is 2022. So you are collecting from 2022, from January of 2022 to December of 2022. Where are you? Here you are. And it will give you all the data. There's Columbus, Ohio. Oh, how very exciting. Okay. Um, and then it's got, um, let's see, blood. But you're going to get your data from here. Um, and then there you are. Here is your average temperature. And then you can go in and you can change it to, maybe let's try 2023. Let's see if we can get a whole year's worth of data. Oh, lovely. Okay. Let's see. Okay, so you're going to have to change it month by month. That's okay. We can do that. It's no big deal. But you're going to collect the data and then you're going to create a regression model and then you're going to submit it on paper and then I'll collect it and grade it for you. Again, use Desmos, build a table, use the regression model, use black Desmos, don't use green Desmos. If you have any questions, come see me in my classroom.